Okay, hi everybody. So today we're going to continue and finish chapter 3. And I wanted to begin this video with a bit of an overview of the whole semester. So I think it's appropriate now, after we took the first celebration of knowledge, in which we celebrated what we've learned in chapters 1 and 2. So just to provide some context here, so if this right here, look, this is going to be chapter 1 here. So chapter 1 is an overview of statistics. Kind of gives us a context what statistic is, at least sort of as a high level summary. So overview of statistics. And we talked about studies and experiments, some other nuts and bolts, sampling, just general stuff. And then in chapter 2, we started talking about descriptive statistics. This was the display and interpretation of quantities. And that was chapter 2. Now, the other side of statistics, as we're aware, is called inferential statistics. And basically, the sort of the holy grail of that is, or the most important thing that we're going to be covering in this course is going to be hypothesis testing. And this is not covered till chapter 9. And so we've got a few things to build up before we can start talking about hypothesis testing. And it starts with probability. So that's chapter 3. Probability. Probability is sometimes referred to as a descriptive statistic, but for our purposes, we're building up theory to get to hypothesis testing. So after you have probability and you study a bit about chance and the probability values, you want to talk after that. You want to talk about random variables. So chapter 4. So chapter 4 is discrete random variables. And this gives us an introduction to random variables. And then chapter 5, once we have discrete random variables, then we're able to talk about continuous random variables. And this is chapter 5. One of the most important continuous random variables is called the normal distribution, and that's chapter 7. Oops. All right. So, chapter 6. So chapter 6 is the normal distribution. And then chapter 7 is an important theorem called central limit theorem. And then and we're going to spend about 2 sections in pretty much each of these. I think we spend a bit more time in chapter 6 because the normal distribution is so important. But chapter 7 is a central limit theorem, and then chapter 8 we talk about confidence intervals. Oh, got out of my box here. Falls. Okay, and so all this here constitutes unit 2. and then we start, this is going to be the third and final unit in the course, is hypothesis testing. And then there's a bunch of different hypothesis tests you could do, one of which is a goodness of fit. And there's just a bunch of different hypothesis tests that we're all going to be able to know how to do. So anyway, so this is an overview. So right now we are here just finishing chapter 3, beginning our ascent to hypothesis testing. Anyway, so I want you guys to keep that in mind. We're getting up to inferential statistics. Okay, so here we go. The main topic that we're going to discuss are the 2 basic rules of probability. So here we go. So key cons. Oh, and I want to see. I should have said this earlier. I want to see this. I want to see you guys draw out some sort of a diagram of this right here, and we'll probably see something like this more. I just want you guys to really understand what it is we're shooting for. Okay. So key concept. In this section, we present the addition rule as a tool for finding the probability of A or B. So we already have kind of an idea of this just based on counting the number of occurrences, which is that either event A occurs or event B occurs, or they both occur, which is the frequency, I guess. Frequency, or number of times, or number of occurrences that either event A occurs or event B occurs, or they both occur. So that's the or is one or the other or both as the single outcome of a procedure. Okay, the word or in the addition rule is associated with the addition of probabilities. That's hence the addition rule. Now there's another rule that we want to look at, and that's the multiplication rule. And that's going to deal with and. So or is addition, and is multiplication, the multiplication rule. Let's see. So the multiplication rule this section also presents the basic multiplication rule used for finding the probability that, which is the blank that event A, which is the probability that events A and event B occurs. In this case, the word and is multiplication. The and goes with the multiplication rule, and that's going to be multiplication. Okay, the addition rule. Here's the notation for the addition rule. We're going to write the probability of A or B. Now, remember, or is addition. A or B is the probability of in a single trial, event A occurs, or event B occurs, or they both occur. This is in a single trial. Okay, so let's look at 2 different events here. This here is later what we'll refer to as a contingency table. I thought I would introduce it earlier because it's so useful in talking about these types of probabilities. So subject uses drugs. Okay, so here's a poll of, let's see how many people. Add these to, what's the total here? Add these, we get 70, 75, so 555 total participants. Okay, so among those, 5 actually used drugs and had a negative test result. So this right here is what we call a false negative. They don't use drugs, but they were tested, and 25 people don't use drugs, but the test said that they do. So this right here is called a false positive. And then these here, they got a negative test result, and they don't actually use drugs. So that's good. So that's right there. That's a true negative. Okay, so the experiment is to randomly just select a subject from the data. And event A is the subject is a person who uses drugs. Event B is a person that got a negative test result. So write A or B in words, find the probability, and interpret its value. Okay, so A and a probability of A or B equals the probability, the randomly selected subjects either uses drugs or got a negative test result. And the computation of this is going to be, well, let's see. They either use drugs, so that's right here. This is so them using drugs, there's 25 plus 480 or that they got a negative test result, and so that's these people as well. So all of this right here. Now, how many of those people do I have a chance of picking? And that is 510, right? That's going to be 25 plus 480 plus 5, and so that's 510 out of the total, which is 555. And I'll go ahead and keep it that way. Well, no, let me just go ahead and get my calculator out and compute this. So 510 divided by 555 is about 0.919. So about 91.9%. That's our empirical probability here. Okay. So the intuitive addition rule, and so we sort of did the addition rule here. Let's just read what it says. Okay, so to find A or B, add the number of ways that event A can occur and the number of ways that event B can occur, but add in such a way that every outcome is counted only once. Count it only once. Don't double count outcomes. That'll throw off the probability. Probability of A or B is equal to that sum divided by the total number of outcomes in the sample space. Okay, now there's a formal addition rule, which is what we have right here. P of A or B is going to be equal to the probability of finding somebody in A plus the probability of finding somebody in B minus the probability of finding somebody in A and B. So that right there is the intersection. That's both A and B. Notice that this probability is contained in here, and it is also contained in here. So it's double counted in this sum. And so we subtract one copy of it out of this in order to get a count of unique outcomes. Okay, so where P of A denotes the probability that A and B will both occur at the same time as an outcome in a trial or of a procedure. Okay, now this is a new thing here. This is this is an example slide. So I'm not going to be grading these example slides. And if you want, you can skip till I'm done. You can skip in the time to where I'm done talking about this example in order to save time. Okay, great. So there's that example. All right, so moving on. When it's on a white slide, I'm going to look for these things being filled in if you want full credit on the slides here. But you don't need to fill in anything on these example slides. That's just a bonus if you want to. Okay, so here's a summary of the key points of the addition rule. So to find A or B, associate the word or with addition. Okay, to find the value of A or B, add the number of ways that A can occur and the number of ways B can occur, but careful not to add without double counting. Okay, now let's talk about the multiplication rule. So in the notation, A and B, now we've seen this before, the event that A occurs in a first trial and B occurs in a second trial. Now that's sort of an important distinction here. We're not assuming that two different events occur at the well, sometimes you can get them occurring at the exact two different events occurring in one trial. We talked about that, but this is sort of a different take on it. You could think about it as having disjoint trials. Okay. Now, and then we also talked about A given B, and that represents the probability of event B occurring after it is assumed that event A has already occurred. Okay, so let's go back to our little table here, this contingency table. This is also a contingency table. And let's take a look at this intuitive multiplication rule, which we'll be discussing further down below. All right, so event A is a Republican, event B is over 50. So write the meaning of A given B and find and interpret its value. All right, same for B given A. Okay. Probability of A given B is the probability of randomly selecting a Republican given the person is already known to be over 50. Given we already know that they're over 50, what's the probability of finding a Republican? Okay, well, what is that? That's going to be, I am restricting my scope here. I'm restricting my sample space to people who are over 50. And I think we already added that up, did we not? What is that, 1107 or no, what, 1101. So this is 1101. Among those, 433 are Republican. And so if you already know that the person that you have selected is a Democrat, is over 50, then there is a 433 over 1101 chance of being a Republican. So what do we have here? That is going to be 433 over 101, which is approximately 0.933. Well, wait a minute. I wrote that wrong. 393, which equals 39.3%. Okay, great. Now, what about B over A? Well, no. Okay, so this is what is this? So this is the probability. Okay, let me go ahead and move this. Lasso that. Okay. All right. Go back. Stop that. There. Move it up here. Great. Now let's come over here. Okay, so B given A is the probability of randomly selecting a person over 50 given that person is already known to be a Republican, given that they're a Republican there. All right, well, what's that going to equal? See, so now I am restricting, let's do this one in green. So what's that going to equal? Now I am restricting my sample set to the Republicans here. And so of which there are how many? Let's just see. So I go to my calculator, I type in 433 plus 427, enter, I get 860. All right, and so that's my denominator, 860. Now, how many of those, how many are over 50? 433. So the total is 860. The ones I'm interested in are 433. And so this is about, okay, let's see, 433 divided by 860. I get about 50%. 0.503, which equals 50.3%. Okay, notice how different it is. A given B, let's see, B given A is not the same as A given B. And we have a good example of that later on. Okay, the intuitive multiplication rule. So to find the probability that event A occurs in one trial and event B occurs in another trial, multiply the probability of event A by the probability of event B, but be sure that the probability of event A, or of event V, is found by assuming that A has already occurred. Okay, so you assume that it has already occurred. And now here, so that's the gist. This is the formal multiplication rule. So, yeah, there it is, right there. I'll put a box around that. All right, now let's talk about redundancy, important applications of multiplication rule. Okay, the principle of redundancy is used to increase the reliability of many systems. Our eyes have passive redundancy in the sense that if one of them fails, we continue to see. We got two eyes. An important finding of modern biology is that genes in an organism can often work in place of each other. Engineers also often design redundant components so that the whole system will not fail because of the failure of a single component. Okay, very reliable. Okay, summary of addition rule and multiplication rule. So, well, here's our summary here. Go ahead and look over that. Now we're going to talk about contingency tables. We've already seen a bit of that. We're going to look a little bit deeper into conditional probability while we're at it. So, okay. Right, and we talk a little bit more about this at least one thing. All right, so complements the probability of at least one. So this is a little bit of what I said earlier. When finding the probability of some event occurring at least once, we should understand the following. At least one has the same meaning as one or more. The complement of this, of the at least one, is no occurrences, so none. That's the complement. Okay, here's a nice summary for you. Find the probability of getting at least one of some event. What you do is so A is the probability of getting at least one of some event. What you do is you look at the complement. The complement of that is that you get none of that event occurring. The probability of the complement. Now, none is very easy to compute because it's just not this, and not this, and not this, and not this. The probability of at least one is very difficult. Because like in our probability with the laptop, with the iPads, it would be the probability that the first, that only the first is damaged. Okay, so only first is bags and backpacks, and or second, or only second selection is damaged by bags and backpacks, or ... or only the 20th. See, so that's at least one is that's at least one. Actually, that's exactly one. So maybe we really don't need the only. So the probability that first is bags and backpacks, or the probability that the second, yeah, that's it. We don't need the only. Or the probability that the 20th is bags and backpacks. Okay, and that is a huge or statement. Now, just to give you an idea, if I had or, there's a formula for 3 things. Probability of A or B or C. There's a formula for that. And it's this: the probability of A plus the probability of B plus the probability of C minus the probability of A and B minus the probability of B and C minus the probability of A and C. You don't need to remember this. Plus the probability of A and B and C. Okay, so when there's 3 sets that we're taking, or this, or this, or this, we get 1, 2, 3, 4, 5, 6, 7 terms when it's only 3. So when it was 2, there were 3 terms. When there's 3, there's 7 terms. How many terms do you think there's going to be when there's 20? You see, so that's going to be a lot. So that is way more difficult than just taking the complement, which is a whole bunch of ands. First one, no. And second one, not bags and backpacks. And third one, not bags and backpacks. Okay, so anyway, so that's much easier to do. So conditional probability we've already talked about. We've talked about the notation already. The intuitive approach here, I think we've... Okay. So we talked a little bit more about this conditional probability. This right here is just nothing other than the statement of the multiplication rule. A and B equals probability of A times probability of B given A. I just rearrange it and I get this. I divide both sides by the probability of A and I get that. I'm going to go ahead and skip this one. Confusion of the inverse, we also already talked about. We saw that the probability of A and B is not the same as the probability of B and A. And here's an example. Look at these 2 events. So D is the probability that it is dark outdoors. M is the probability that it is midnight. So it's just 1 point in time. Notice that the probability of it being dark, given that it's midnight, is 1. It's certainly going to be dark outdoors if it's midnight. On the other hand, what's the probability of it being exactly midnight given that it's dark outdoors? Well, 0. I mean, it's hardly anything at all. So they are as different as can be in this example here. Okay, and the rest is just something you can look at. We're not going to go over it, but you're welcome to read it. And sorry that took so long. You have a wonderful day. Good luck on the quiz.